So thank you, everybody, for coming. There's a lot of people in here. My name is Derek Nelson. I'm one of the core developers of PipelineDB, and today I'm just going to give you an overview of what the product is, what it does, and then sort of take you through a tour of the internals in terms of how the system works end to end. Just as a show of hands, has anyone used PipelineDB in here? Kenny? Nice. Okay. So as I said, at a high level, what is PipelineDB? And this, at the simplest level, PipelineDB is a system that allows you to run continuous SQL queries on streams. And we call this abstraction the continuous view, which you'll be hearing me mention quite a few times during this presentation. And you could essentially think of continuous views as very high throughput, real-time, incrementally updated, materialized views. The fundamental difference between a continuous view and a materialized view is that a continuous view actually doesn't store the underlying data that it needs to build itself. So that's one of the fundamental principles, fundamental design principles of PipelineDB that you'll learn more about in this talk. And so why are we here at the Postgres conference? Our product's based off of Postgres 9.4.4. So there's no special client libraries, no proprietary libraries or anything like that. We have a full streaming capability using all the libraries that work with an existing Postgres installation. And that's something that we're pretty dedicated to maintaining. So right now it's a fork of the Postgres core, but almost all of our code at this point has been factored out. So in the medium and certainly our long-term intention is to completely factor out PipelineDB as a standalone extension of PostgreSQL. And of course, the product's free and open source. It's licensed under the GPL v3. So we have a GitHub page. You can download it, install it, use it however you want. It's basically, a lot of people ask how complicated is it to get up and running, and it's comparable to just installing PostgreSQL essentially. So if that gives you an idea of what that's like. So the 100,000-foot view of the problem it solves is pretty generic. Any data pipeline, as all you know, at one end of the extreme, you have very voluminous, highly granular machine data that's being produced very quickly. It's raw, it's not aggregated, it's dirty. And then at the other end of the extreme, the consumption side, you have charts, graphs, highly distilled presentations of this originally messy, granular format that humans can actually interpret and use. Humans don't read granular data, and so we all have this magical processing step in between. And PipelineDB aims to solve that processing layer that bridges the gap between highly voluminous granular data and consumption using just SQL. And it focuses on being very, very good at any sorts of queries that are performing aggregations, filtering, anytime you want to look at a sliding window of time worth of data. And so most generally, PipelineDB is about continuous reduction. So if you're ever confused at any point in this talk, just ask yourself, how does this relate to continuous reduction? That's pretty much the fundamental basis of the system and what makes it useful. So an important question to ask is why we built this in the first place. Our team has very deep experience building very large-scale stream processing infrastructure when stream processing was still a relatively new thing. And we used pretty much every open source system out there. We built a lot of things ourselves. And ultimately, everything ended up sort of looking like something like this. There was a lot of duct tape, a lot of one-off solutions, and it was really messy, difficult to manage because a lot of these things are still very new. And so ultimately, PipelineDB is meant to simplify that layer of processing that is typically known as very complex, cumbersome, burdensome. And we do that by putting a continuous view between data production and data consumption. So this simplicity is nice, but it has to have something more to be useful. Obviously, continuous SQL queries are pretty unique. So they do give you more than just simplicity. So the first one, the most fundamental one, and sort of the other ones kind of are derived from this, a continuous SQL query allows you to aggregate data before anything is ever written to disk. And so if you think about like typical ETL jobs, batch ETL jobs, that's really what they're doing. They're taking granular data aggregating it, then writing it to some database. And with continuous queries, you're able to do this continuously, send information directly into the database, and where it can be continuously aggregated and then written to disk once it's as small as possible, which has obvious performance benefits. So what that means is if you think about this extremely simple continuous query here, select count star from stream, over time the data volume, this purple line here, might grow exponentially or it might grow very, very quickly. But with continuous aggregation, the size and complexity of the database can actually remain constant. And that can be a really powerful thing because you don't have to rely on scaling your infrastructure out, adding a bunch of new nodes as your data volume increases, because the output of these continuous views is the only thing that's stored in the database, and it's typically much, much more dense than the input to the continuous views. So that differential between the size of the input and the size of the output, our system exploits by maintaining this level of size and complexity that's essentially independent of the amount of data that's been pushed through the system. So a second major benefit of continuous queries, and this is probably the most popular thing that our users use the system for, are sliding window queries. So this allows you to look at information that's only relevant within a predefined window of time. So in this case, you can define this query with a max age of 1 hour, and anytime you select from this continuous view, the only data that you'd see is guaranteed to be only relevant within the last hour. So anything that's outside of that window is physically removed from disk. In the background, it's trimmed out at read time. And so you can essentially think of this as a sort of automatic TTL on SQL tables. So another major benefit that we see people use a lot with our system is continuous queries allow you to run probabilistic computations on infinite streams. So if you want to estimate the cardinality of a stream of user events and that stream never ends, it's impossible to do with perfect accuracy, obviously, but you can run continuous estimations on that information very efficiently. You can of course use these sorts of estimation algorithms on regular tables too if you wanted to, but you obviously can't have an infinite table that never ends. So these sorts of things end up being really, really useful in the context of stream processing. So Pipeline supports things like top K, percentiles, distincts counting, large set cardinality estimation, all that sort of stuff on infinite streams with no sorting. And the trade-off is you get a very, very small margin of error, typically less than 1%, which for most stream processing use cases is more than sufficient. So to give you guys something tangible to hang all that on, I'm going to show you a couple of queries here. So this is a tool we have called Padhoc. It's a way to run ad hoc queries on streams, and this helps people develop and sort of tune continuous queries. And a lot of times people find it beneficial to use to debug streams. Yeah, do you have a question? Oh, sorry. Is that good? Okay, sorry. A little more? Okay. Yeah, sorry about that. So this allows you to run ad hoc queries on streams, which is kind of a weird thing because the stream never ends, but I'll show you what it looks like. So there's no data coming in yet. I'm going to run this script down here is just generating basically a bunch of random integers. And you'll see as I stream those through the system, you'll see all this stuff just update automatically. And it's not very useful to have like a query that's constantly changing like this, but this is to illustrate what an actual continuous view looks like on disk. You can pause it, of course. So that's the only thing that's actually stored on disk are these aggregate values. The query is not being rerun on the client or anything like that. That's all that's stored on disk. And so this query is a sliding window query that I mentioned earlier. Very, very simple one, obviously. So it's the second one down here, V1. It's just going to select the count from the stream within the last 5 seconds. So I'll just do a whoops. So now when I select from this thing, you'll see the count increasing, obviously. And then if I stop selecting from it, or inserting, you see the count just shrinks down again because the 5-second window has passed and I haven't inserted any new information. So this should go back down to 0 again. And then obviously this works for the entire suite of SQL, so it's pretty useful. I'll show you another demo at the end of the talk that's a little more involved, but that's just to give you guys something to hang this on for now. So now we're going to dig into the internals. I'm going to start at where data originates, where it comes into the system, and then I'm going to talk about how it moves through the system, how it's processed, and ultimately how it ends up in a continuous view where it can be read by some client. Before I dive in anymore, does anyone have any questions about anything at a high level? Sweet. Okay, so streams internally are actually a foreign table. When we first started developing the system, streams were a much more special thing, and anytime you inserted into a stream, it was intercepted in the execution path, and it had kind of it was treated specially. And we moved away from that for a couple of reasons. One, it caused a few special cases to be necessary throughout the code base that we weren't happy with. But the main reason is that it's helping us move to a completely factored out extension. We're trying to use as much of the extension APIs as we can. And it makes a ton of sense to have streams be foreign tables because they essentially behave exactly like tables. So this was really natural. So there's a system-wide foreign server that you need for a foreign table called pipeline streams. You'll see that in every database in PipelineDB. It exists by default. And then we simply have a foreign data wrapper that reads from and writes to what we call the stream buffer, which is where all this streaming information begins. It's where the processing always starts, and we'll talk about that in a second. So there's no permanent storage with streams. When you write to a stream through this foreign data wrapper, there's no permanent storage. It gets written to the stream buffer, and then that event ultimately is ephemeral. As soon as it's been read by whatever needs to read it, it's just clobbered, and new incoming data overwrites it. So stream rows only exist until they've been fully read. And this at the top is sort of the high-level flow of this part of the internals, the first phase. Data arrives at the stream buffer, so that's where we are now. And these just look, as you guys saw, these just look like a regular insert into a table, insert into stream. And they ultimately go through this foreign data wrapper and end up in this stream buffer here, which is essentially a huge pre-allocated block of shared memory in the system that all these different processes that I'll mention read from this thing. So it's a giant shared block of shared memory, and it's a concurrent circular buffer essentially. So what that means is a data point comes in after this insert, this heap tuple you see here on the right, and this bitmap on the right corner of this thing. Each of those bits represents a continuous view that needs to read that particular event. And as soon as every single continuous view that's interested in this event has read it, all of them get flipped to 1, and at that point, any new incoming data can overwrite this this dead row, essentially. So that's the nature of what makes this thing circular. And all the appends are contiguous, so every new incoming event goes directly after the last one, which makes the writes fast. Yep. Sure.
So is a stream that is being thrown into the system, is it going through your postmaster, or is your foreign data wrapper processes actually receiving the stream?
So his question was, for a stream insert, is the insert going through the postmaster or like the regular insert path, like any sort of table? Is that what you're asking? Yeah, so it goes through the regular insert path. Before, as I said, it actually had a special path, which was different, but now it goes through the same exact insert path as you'd see for inserting into a table or any other foreign data wrapper. So, yeah.
So that means it goes through your shared buffer of Postgres, and then
So it's just like a regular, it's the exact same as if you'd be writing to a table, except in the foreign data wrapper, instead of doing like a heap insert or actually writing to the table, that's when it writes to the buffer inside of there. So that's what the implementation looks like. Yeah, thanks. So that heap tuple can be evicted now. And the next stage of the ingestion process involves running a query on a micro batch. And this is done by a process type we call worker processes. And these things run as just regular Postgres background workers. And this is another part of the sort of extensibility API that helps us basically turn Postgres into whatever we want. You can have processes that do whatever you want now. And we use those for all of the different worker types that comprise our system. So the worker process reads from streams. And those worker processes are essentially running as background workers. So it just uses the regular background worker API. Those things start up at system startup time and essentially just start reading from the stream buffer as fast as possible. So we're at the second stage here now. This worker process that's running as a background worker is running. I'm going to keep this query simple just to make things easier. So this is just like a select count star average from stream. And this worker process is continuously executing this query on batches from the stream buffer. So it might read 1,000 at a time, run this query plan on that micro batch, and then generate what we call a partial result. So this is the overall flow here. You'll see the stream scan plan is from our foreign data wrapper, just implements the get stream scan plan. And the basic logic is read as many tuples as you can from the stream buffer as fast as possible until you hit the batch size, then run the query on it, and then whatever the output of that partial query is, that's what we call a partial result, and that leads in to the next phase of the internals. So here you'll see it's the count, you're doing a count and average. You get a count, which is simple, and you'll see the average here actually isn't an average, and this is an important part of how our system works. So all of our aggregates in the system, anything that's more complex than simply like incrementing a count or a sum or something like that, we actually store the transition state of the aggregate. So if you've ever created an aggregate function in Postgres, you know that you have to specify some sort of transition function for a lot of aggregates that take in an input value and then they update some internal state that allows that aggregate to be updated further based on new information coming in. So that's the actual state we store for aggregates in the database. And that's why the transition state for average is just it's a count and a sum, which is what you see here. And so for parallelism, these are the worker infrastructure is highly parallelizable. No matter how many workers you have, each one essentially gets a disjoint block of this stream buffer, and that's all it reads from. So all of these events are essentially round robin between a pool of workers that are reading from the stream buffer. So it's very parallel here. So that's the first phase. We've written to the stream, read from the stream buffer, and executed the first stage of the continuous query plan, which generates this partial result, which stores the aggregate transition state. And the second phase of the overall continuous query process is much more interesting. So this is the incremental update phase when we take all these partial results coming in from all these different workers and we merge them with whatever's on disk. So it's a little bit more complicated. So let's dive into that. So we have this notion of combine functions. Any aggregate in a PipelineDB continuous view can be combined. And basically this is the form of the function. So combine is a function that takes two transition states and returns one transition state. So this effectively allows you in general to incrementally update any aggregates with any sort of partial result coming in. So when you hear me talk about combine, that's effectively what's happening. And we do this with a new catalog table we've added. We haven't changed any of the PG aggregate catalogs or any of the aggregate functionality whatsoever. We have one catalog table that stores all this metadata. It stores all the functions that tell the system to take one aggregate and figure out how to combine that aggregate with other aggregates. And that's essentially just a matter of looking up the right functions. So you can also have any user-defined aggregates are fully combinable as well. you just have to pass this combine func, which is basically what you see on the top row here, some function that takes 2 transition states and returns 1. So starting from the last phase we were at, we ended up with what we call a partial result or a micro batch result. Those terms are interchangeable. We have the result of the continuous query plan after being executed on a batch of streaming tuples. So we have a count of 1,000, then our average transition state. And at a high level, this is what happens with combine. So this row on the bottom comes from disk, and this combine stuff, so ultimately reads everything on disk that's related to this incoming micro batch, and then the continuous query plan is executed again on this combination of tuples, and you get a combined result. So you'll see here we actually have enough information to produce a combined average based on 2 existing aggregates, because again we only store the transition state in the database. So this is a high-level logic. One of the hardest parts about this combine phase is actually looking up the existing tuples that you'll use to update against the incoming micro batch. So the high-level logic is first we get a plan, we generate a plan that's as fast as possible to do that lookup based on what the incoming micro batch looks like. And we do that by looking at all the incoming values, let's say you have groups X, Y, and Z, you only need to update those groups that have the same keys. So we generate a plan based on all the incoming values, and then we essentially run this lookup plan on using it. And I'll talk more in a minute about how that works. So again, this thing needs to be as fast as possible. This is definitely a bottleneck in the system because it's touching disk. It's reading from disk, it's writing from disk. That's what the combiner does. So we've done a lot of work to really tune this thing pretty well. So at first, obviously this has to be indexed. At first, when we looked at a group, we would just, sometimes we tried just randomly picking a column, then we tried indexing on the entire group. We tried a few things, but it's very difficult to pick the right index because this index is created when you create the continuous view. So you don't know anything about the statistics or the distribution of the actual groups, so you can't really do anything particularly smart. The best solution that we've found that actually works really well is instead of looking up the actual group, we look up a hash of the group. And so that every incoming group gets hashed to some 32-bit integer, and that hash is actually used as the index key. And that effectively allows us to maximize the cardinality of the index of this table, even though we know nothing about the distribution of the group itself. And empirically, this works really, really well. It's great for random lookups. The downside is that you obviously have to deal with collisions. But since all of this stuff is happening programmatically in this combiner process we have, it's actually not a big deal to just trim out the collisions after the fact and go from there. It's pretty straightforward, and it works really well for us. And so a lot of people are doing groups that involve some sort of time component, like you see here, select day, group by day. Almost all groups, very often at least, will contain some sort of temporal component. And we can exploit that to actually do a little bit better with this group up plan by using essentially locality-based hashing instead of just standard hashing on the group. So for any group that contains a temporal component, we actually use a 64-bit hash. The first 32 bits are the same as the previous hash, just the regular hash of the group. And then the highest order 32 bits are actually the timestamp, the integral representation of the timestamp of the key. And since this index is essentially sorted, most of the groups, presumably, as they're being updated, are going to be relatively close to each other within the index. So this gives us really, really good caching locality for any sorts of queries which involve a temporal component in the key, which turns out to be a huge majority of them. And obviously the downside of this is that the index is twice as big, essentially. But it's worth it. Okay, so to recap, I kind of went off on a tangent there talking about the lookup plan. So at this point, we have the micro batch result from the first phase from the worker processes, and now we have the existing data on disk that already exists in the continuous view. So that's where we're at. And this is basically the logic of how the rest of the combine process works now that we have all of that information. So we get the plan, it looks like this, you combine everything, union with the micro batch and the on-disk results, and then if it's a new tuple, we just do an insert, and if it's an existing tuple, we just do an update. And so the combiner parallelism is a little bit different than worker parallelism because they're touching rows on disk, so this part isn't as simple. Originally, one combiner could only ever update one table, but the latest version, we've done a lot of work to make that better. So now on-disk groupings are actually sharded by group. So what that means is that each row on disk is guaranteed to only ever be touched by a single combiner process, which is an assumption that we really take advantage of in the internals of this part in terms of optimizations and making it faster. That turns out to be a pretty powerful assumption to be able to make. So, I'll show you guys a little more interesting demo than before. So we have this, I'll just leave that closed for now. We have this data set that's essentially all Wikipedia page view traffic for a given day, summarized by hour. So it's aggregated down by hour. And we're going to run this query on it here. So what this thing is doing is, so we look at the project, the text, that's just like the project code, like English Wikipedia or something like that. Then we just do a basic sum. And then this part's a little more interesting down here. This takes advantage of one of our probabilistic data structures called filtered space saving, top K. So we're going to look at the top three website, basically top 3 pages by project with this query. So first I'm going to create the stream. And to get data in, I'm just using, so I'll show you this small, it's a little bit small, I know, but so we basically have this as a stream on our website. You can use, the stream's compressed, we're piping it into unzip, and then in turn piping that into pSQL using copy over standard in. So that's how we're getting data into this particular continuous view. So that's coming in. Then you should be able to see all these top K is changing. They're probably good. I think these things are like sorted. So this is it's kind of hard to see with the thing there, but so we're essentially doing top K here. But these are the rows you see here are the only thing that's actually stored in the database. So typically to do top K with perfect accuracy, you need to keep everything, sort it, and then trim off the top K. Here we're doing it with just this data you see here in the database, which is obviously much smaller. And then another cool thing you can do with the combine infrastructure is any users can combine any aggregates they want as a special aggregate. So you'll see here, I'm going to get the top K titles from all of the stats combined. So obviously it's a garbage title. I don't know what those pages actually are, but so these top Ks are the same as if you took all the information as one input stream and ran top K on that. But we're actually doing this by combining only the rows you see here, which are much smaller. I don't know what that is. So the last part, there are a lot of things you can do to make the system a lot faster. We don't tune it to be very aggressive by default, just how Postgres doesn't really tune itself to be very aggressive either. So I just like to go over a couple knobs you can pull to make the system faster. The first one is continuous query num workers. This controls the number of worker processes that can be reading from the stream buffer, essentially. The other one is num combiners. These are the processes, the second part of the internals that we talked about, doing the incremental updates. This is the number of processes that can be doing that in parallel. This continuous query batch size, this is how many tuples each worker process will read from the stream buffer at once, which if you're getting a lot of aggregation, this is probably the best thing you can tune. The bigger the batch size, the more the worker process will be able to shrink that down relative to the input. And these ones are kind of new actually too. The step size, these are for sliding window queries, which as I said have been pretty popular. The step size is the granularity of how the window is moving forward in time. So if you want it to move forward every millisecond, we actually have to store a lot of extra data. But if you don't care about the window sliding forward every millisecond, you can actually tune that with the step size here. So this continuous view has a window size of a minute, but it only steps forward every second, which makes it pretty fast. And the step factor is the same thing. This allows you to express that step granularity as a fraction of the overall window size. So if you wanted to say only tumble the window forward after it's reached 10% of the overall window size, that's what the step factor does for you. Okay, so that's it. If you guys have any questions, I think we have some time. I'd be happy to answer anything. Yep.
So it looks like you're using hash indexes.
Mm-hmm.
Are there problems with replication using those?
Yeah, so we actually don't use hash indexes. We use the hash values on the B tree, and the B tree implementation is so good and so mature that it's actually way faster, and then you don't actually run into the problems of the wall problems that the hash indexes have and stuff. So yeah, it's actually hashes on top of the B tree. Yeah. Yep.
When you're suggesting stuff onto that shared circular buffer,
Mm-hmm.
what do you do when you run out of space? You can't keep up with the incoming stream.
That's a good question. So his question was, with the circular stream buffer, what do we do if there's no free space in the stream buffer if a client's still trying to write to the stream? And the answer is we block. We don't let the client finish the write. It blocks. And that actually turns out to be a really useful property in a stream processing system. When you don't have that capability, you get queuing, which is obviously really bad. So our design decision is to just block. We just make the client wait until there's space. Good question. Yeah.
Do you have any experience on the performance impact on a server when you use quite a lot of continuous views and streams?
Mm-hmm. So his question was what is the performance impact like if you're using a lot of continuous views and streams? And it's hard to answer. It depends on the queries in general. If you're running a lot of really, really complex queries, there's obviously going to be a pretty big performance impact, but it really depends on how complex the queries are. Most of our users saturate the network interface of the server before saturating the system itself. So that's typically like a good bound to sort of estimate performance on, is whatever the throughput is. Yeah.
If you have a slaving something to use stream replication, how can we fail or from the
So there's no, you can do standard replication with pipeline. It's we have a guide on our docs, but it's basically similar to the way you'd fail over with standard Postgres. It's almost no different. Yeah, but it's definitely possible. Good question. Yeah, Kenny.
Can you talk about crash recovery? Like, is there anything special and with the circular buffer? How do you recover from that?
Yeah, so his question was crash recovery. Do you mean like workers, combiners? Yeah, so about crash recovery. So anytime there's an unrecoverable error, which is basically a seg fault, is the only thing that will actually crash the system. All the processes will die, and they'll ultimately be restarted by the postmaster. And under those conditions, you could potentially lose data that's in the stream buffer. That is possible. So the unit of data loss is essentially how big you want the stream buffer to be. In the worst case scenario, you could lose one stream buffer worth of data. And any other sorts of errors all other errors are recoverable. So those won't affect anything. It's basically there's like a try-catch statement in the worker and the combiner. So the only thing that will really that could really cause data is essentially a crash, a seg fault or something like that. Yeah, please.
So if you were like consuming from Kafka, for instance, you'd want to actually catch that and then retry those events.
Yeah, so his question was if you're consuming from Kafka or something like that, if there was a crash, you'd want to try to reconsume those events or something like that. Yeah, so there are a lot of different ways you could do that. Obviously, it's a tough problem. We do have a built-in Kafka support, a Kafka extension. I don't know if you were using that, but it actually handles all of the consumer offsetting, partitioning, parallelization, all that stuff itself, and stores all of that state durably in the database. So when the system came back up, it would pick up wherever it left off. So that's also a tool you can use. Yeah, thanks. Any more questions? Yep.
When you deploy this sort of thing, is it typically like an extension on a usual table-based production database that also does streaming, or is it normally like a separate database that you send stream data to and associated with that?
Yeah, so his question was, are deployments typically, is this typically co-located with like a regular sort of production OLTP operational database or something like that, a more traditional database? You can do that, and you can store regular tables in Pipeline just like you can in Postgres. Most of our users are using it almost exclusively for just very high throughput continuous views. So for any sort of like OLTP workload, I'd probably recommend just keeping it completely separate, unless the load on the PipelineDB server is not that much. You know, if it's only like a tens or a couple 100,000 events per second or something like that, it's probably not going to be a huge deal. But in general, it's probably a good idea to keep them separate. Yeah.
Is there any advantage to, say, doing joins between the kind of materialized aggregates of the streaming data and regular tables with your operational data?
Yeah, so you can actually do stream table joins. So you can actually include you can actually solve that problem with the continuous view definition itself. So what we see a lot of users doing is like augmenting streaming data with a table. So they'll join the streaming event on the table by like user ID, and then they'll have like the username from that, and that will come from a table. So you can join streams on tables with continuous views, and that's pretty popular and pretty useful. You can't join streams on streams. We don't support that yet. I don't know if we ever will. It's kind of a hard problem, and so yeah. But streams and tables you can join. Did that answer your question? Yep. Okay, thanks. Anybody else? Yep.
How high on your roadmap is turning this into a proper extension?
I would say within 6 months, probably. Yeah. Most of our it's something. Every new piece of code we write is independent of the core, and we also rip code out of the core on a regular basis. So we actually don't have that much stuff in core. It's actually kind of one of the problems is like parse time hooks. We have like create continuous view syntax. Postgres will probably never have parse time hooks because it could conflict with like other extensions that overrode it or something like that. So we'll have to see about how we handle that, but it's fundamentally not like a complex problem for us. We'll be there pretty soon. Yep.
What kind of event volume do you see in your implementations?
What kind of?
Event volume.
So his question was, what kind of event volume have we seen in our implementations? We have, it ranges again on the complexity of the query, but most power users who are doing reasonably complex queries, anywhere from 250 to a little over 1 million events per second on like one server is pretty common for power users. Yeah. Anybody else? All right. Well, thank you all for coming.